So today we'll be having a look at the evidence for the existence of subatomic particles besides that of protons, neutrons, and electrons. So why would we care about this? Well, the analogy that I like to draw is, last time we saw the evidence for things that made up protons, right? So we had the quarks inside our protons. This might be a bit analogous to scientists discovering that, wow, if you look inside, let's say, a silver atom, you can find, oh my god, there's a nucleus inside with like protons and neutrons, and there's some electrons whizzing around, right? That's crazy. Last video we discovered that there was stuff inside a proton, but we can also discover that there are things besides. There are subatomic particles besides protons. So, we can discover things like neutrinos, like positrons, like pions, like kaons. And the analogy to this is, before we might have only known that, hey, we have a silver kind of particle, we only know that silver exists, but now we find gold, right? We found some gold, we might have found iron, so we found other elements, kind of. So what kind of evidence will we find? So before we dive into discovering the positron, the neutrino, as well as discovering pions and kaons from cosmic rays, the first thing that we'll have to quickly discuss is that of the cloud chamber. So this is an example of a cloud chamber. Now, what do we make it out of? So what we have is this container. Inside it contains isopropyl alcohol. And when we have the it's kind of like rubbing. Your dad might use it to clean something. What we do is we evaporate the isopropyl alcohol into this container, and then we cool it down to -30 degrees. Now, at this temperature, the alcohol should condense back into a liquid. But because there's no nucleation sites, it doesn't quite become a liquid. For example, you might have seen those TikToks where there's like a bottle of water, but it's liquid, but then when you open it, it freezes. That's because there was no nucleation sites. It was too smooth for the ice to begin forming. Similarly here, it's a very smooth surface, so there's no ability for the isopropyl alcohol to condense into streaks until we can see the radiation coming through here. And so what happens is that this thing here is an alpha emitter, I believe. So it might be like a stick of uranium. And this thing is emitting alpha particles shooting outwards. Right? So it's pretty cool. It's a tool that we can use to visualize the radiation given off by a source. And this is really important because we didn't have fancy technology back then to visualize it. So back in the 1920s and 30s, this is really important. Even all the way up to the 1970s and 80s. So what happens is that when you have these alpha particles or any other kind of ionizing radiation, what they do to the isopropyl alcohol is that, I'll draw some isopropyl alcohol here. And what the alpha particle will do is that it'll either hit the isopropyl alcohol or it can hit an air molecule, for example, N2. And what it'll do is that it'll cause it to become, either this to become charged or this to become charged. And because the isopropyl alcohol is it's a charged it's a polar molecule, right? Because this is going to be, oxygen is partially negative from chemistry and hydrogen is partially positive. So we're going to begin to form the isopropyl alcohols are going to begin to congregate about this charged molecule. And so what that does is when you have all these alcohol molecules congregating around this charged air molecule, it begins to condense, and that's why you can see these streaks. So what the alpha particle has done is it ionized the air molecules all along this path, causing causing the isopropyl alcohol molecules to condense there and leave a visible streak. So we now know what a cloud chamber is. Sometimes you can even put a magnetic field over it, and because the alpha particle is charged, it'll go in a spiral, which is pretty fun. But let's get on to discovering how we discovered the positron. So first of all, what is a positron? Well, a positron is just a positively charged electron. A positively charged electron. And it's typically given the symbol E+ instead of E-. So how do we discover this? Well, it was actually first experimentally postulated by our friend here. His name is Dirac, who's a brilliant physicist. He did a lot. In fact, one of the biggest things that he did was that he, in Dirac's equation, he merged special relativity with quantum mechanics, which was a big achievement at the time. Still, it's a big achievement because it merged two very separate and very important areas of physics together. And when he was solving his equation, he got, so when he was solving, so when he solved his equation, he got both a positive and a negative answer for the electron. So kind of like you might be in math and you get a positive and a negative answer for the time. Now, instead of just throwing away the positive electron, he actually thought about it, and he said that, and he actually believed that there were these things that were positive electrons that would balance out his equation, would work quite nicely. People didn't believe him until we had the experimental evidence. So what is the experimental evidence? Well, remember that cloud chamber that we had before? What we did is we fired some electrons into it, and so the electrons would take a typical kind of path. They would kind of curl this way. When you fired, and then we found some sources that could release positrons. Not that we knew that they were releasing positrons. They just kind of put everything into this cloud chamber and looked at it because they were just kind of excited. And so what they saw was that it looked kind of the exact same, but just in the opposite directions. The really important thing to note here is that the radius of curvature is the same. Why is that important? Well, that indicates that these things have the same charge. Remember that Fc is equal to Fb. So therefore, we can actually create Q on M is equal to B on RB. So here we can see that if they have the same radius and the same magnetic field and the same velocity, we can say that these two things have the same charge to mass ratio, but have different charges. So this is pretty convincing evidence that the positron really existed, which is very exciting. It showed that Dirac was right. So the next particle we'll be looking at is the neutrino, which I believe, if you look at the name, neutri kind of gives you a feeling of it's neutral. Ino, I believe, is Italian for small. So the name, I believe, in Italian means the small neutral one. And that's because the neutrino is a very, very small particle. It's believed to have either no mass or like a tiny, tiny, tiny amount of mass, like billions of times smaller than that of an electron. And right now, there are billions penetrating through you right now. Because the neutrino is not charged, and so it can easily pass through our bodies without moving at all. It passes through the whole Earth and just flies on through. It's a crazy particle. It doesn't do anything. So let's understand a bit more about the neutrino, where it came from and why we thought it existed. Let's have a think about beta decay. So beta decay, it kind of goes along the lines of this. We have a neutron turning into a proton and an electron. The electron is called the beta particle. This is beta minus decay. Now, this is fine. This is fine. The problem with what happened is that if we measure the energy of the electron, so we measure the energy of the electron and we kind of graph it. There's the kinetic energy of electron. And on the vertical axis, we have the frequency. This is not frequency like the frequency of a song or like frequency of music or the frequency of a note. This is frequency in a mathematical sense. So like the frequency of red cars just means the number of. And so when we graph it, it looks something like this. And the peak might be, say, 1.16 mega electron volts. Okay, so this is an interesting graph. So we can see that the maximum kinetic energy that we saw an electron ever emit when it went under this decay is 1.16. And that's the maximum kinetic energy. So that, as in, this decay must release some determinate amount of energy. So we can conclude that this must release, that the kind of energy of this reaction is 1.16. Every reaction should release 1.16 mega electron volts. That's cool. But think about maybe some guy over here. You know, there's quite a lot of them out there over here. 0.5 mega electron volts. So this energy here from 0 to 0.5, this is for the electron's energy. But if we think about from 0.5 to, because this reaction released the 1.16 mega electron volts, where is the extra 0.66 mega electron volts gone? Why is there missing energy here? And so a man called Pauli Wolfgang said, okay, you know what? The way to solve this must be that there is a neutrino. There is a third particle that is emitted, and this part here, the 0.66 mega electron volts, goes towards our neutrino. The neutrino will take it away as well, and that solves all the problems that we see here. And so, and this character that I've drawn here is the Greek letter vu. It looks like a V, but it's not quite a V. And that is our neutrino. In the particular case for a beta decay, it's actually an anti-neutrino. If you had beta plus decay, it's a neutrino. So what else did they do? They also looked at what cosmic rays produced in our cloud chamber. So again, we have our cloud chamber. And what they did was they just put it on the top of a tall mountain, and so there's a lot of cosmic rays hitting it, and cosmic rays are just basically gamma rays, really. And these gamma rays kind of hit our atmosphere, and they generate all sorts of crazy particles like pions and kaons and lambda particles and all kinds of crazy particles, right? And so they all come whizzing through here. Now, each of these has a particular kind of idiosyncratic mass charge combination. So they might have the charge, the right radius, the radius of a proton, but in the wrong direction. So a proton would have gone this way, but this one goes that way. Or it might go the same way as a proton, but in a much bigger radius. Or it might go in the same direction as a proton, but with a much tighter radius. The point is, it's very chaotic. They saw all of these crazy tracks being produced that were definitely not by protons or neutrons or electrons. And so because of this, they began to hypothesize, this was evidence that there were things that weren't protons or neutrons or electrons, because they did not have the charge to mass ratios or the right radiuses. And hence, there were other things that were subatomic besides protons, neutrons, and electrons. And that's all the evidence that we have. In the next video, we're going to go through some details about the Standard Model. See you guys there. We offer physics, chemistry, and math tutoring. For more insightful explanations like this one, head to tutorgum.com.